All right. Well, thanks, Eze, and thank you to the organizers for inviting me to speak here and also for having me here at IMPA these past 2 weeks. It's been great, and the time has gone really fast. I can't believe it's almost over. So I'm going to talk about some of the computational dynamics work I've been doing in Sydney with Gary Froyland at UNSW and Geir Gottwald at the University of Sydney. And so the thing we're looking at are these slow-fast systems. So I'll start by giving an example of a slow-fast system, or a multi-scale system. And to do that, I'll do one in a field that I've given way too many talks about, which is a partially hyperbolic example in the 3 torus. So if you start with, say, the cat map on T2, this moves around very chaotically in the torus. And you can cross this with, say, the identity on S1. And if you look at this system, if you just start with some point somewhere, it'll be in an invariant torus. And if you project down onto the S1 coordinate, you just have some, I'll call this X. You have some point X, and this isn't moving at all. So this is maybe a dead, slow system. Nothing's really changing in X, but this is moving really fast. So what happens if you perturb? And so you look at some system very close to this one. And now your X variable, because you've perturbed, it'll start moving from iterate to iterate. So you'll have, at each point, it's moving very fast and chaotically in these variables on T2, and it'll start moving here. And in this case, how it moves, whether it moves slightly to the left or the right, depends on where you are up on this torus above this x-coordinate. And because the Anosov's moving very fast and chaotically, it's almost like you're just randomly sampling from some value here. So it's like you're randomly choosing whether to go left or right. And you can look at sort of the mean and the variance of this distribution up here, and it looks a lot like you're just sampling from some distribution with a mean and variance. And if you look at the orbit, so say you're starting at some point Z, if you look at the orbit Fn of Z and project, this gives you some sequence. This sequence looks like it's evolving according to some sort of drift diffusion process. So it looks like this thing is just sampling from some system like this, a stochastic differential equation, where this is the Wiener process, this is just Brownian motion. And people have been observing this in practice for a while. If you have some complicated system acting on different timescales, often there's some sort of chaotic fast behavior. And in order to approximate the system by something lower dimensional, they just look at this and observe that it's behaving a lot like noise, and they replace it by noise, and then analyze the system that way. And so this has been going on in practice for a while. And the rigorous theory as to why this works has sort of been catching up. So there's a lot of work in this, which is called homogenization theory. And if I give, to sort of put this on a more rigorous backing, if I start with some function alpha from S1 to R, and another function g from T2 to R, so that the average value of g with respect to the invariant measure is 0, you can define some system of maps by A, B, here's the Anosov, and X plus 1 over n alpha x plus 1 over root n g of v. If you look at this sequence as n goes to infinity, it's just going to A cross the identity, because these terms just go to 0. But instead, if you look at some iterate, fn to the n, does it make any sense to say how this is converging? And certainly in any usual C1 topology or whatever, this is not converging because this first coordinate, you just have an to the v. But this basically averages out, and you're left with some sort of process here. And you can define a notion of convergence, a pathwise convergence, to the system here. And in this case, G will give us a constant diffusion beta. So this beta value depends on the function G. And to show this rigorously, it's been done, I believe, the first rigorous proof is by Geir Gottwald and Ian Melbourne, published this year. But it's based on a lot of other homogenization work in other settings. So here it's because we have a deterministic discrete time map, but in other cases, all of these other people have proven lots of stuff. All right. And I'm using an Anosov on T2, but certainly you could do it in more general settings for both of these manifolds. You could have any sort of Anosov system or an axiom A system, certain partially hyperbolic systems. One thing in the continuous time that people often study is a Lorentz flow. So you look at the Lorentz flow forcing some other system. The important thing is that you have some sort of exponential decay of correlations going on. All right, so this is an example of one of these slow-fast systems. And our question, what we're trying to work on, is if you have some sort of system and you believe it's a slow-fast system, is there any way, without knowing any sort of a priori knowledge of the system, to solve out what the fast variables are, what the slow variables are, and what this projection P is? So in order to sort of define this question, I'll introduce what I'll call the slow-fast framework. So you have some space here, Z, the phase space of your system, and you have some dynamics, T, acting on the system. And I'm writing this as if it's a discrete time deterministic map, but in general it could have stochastic behavior. It could be continuous time system if you want. And then there's some projection down to hopefully a simpler space X with S. So here S is your slow dynamics. And again, I'm writing it as if it's some deterministic map, but in general it's probably something like this, some sort of stochastic system. And now, what do I want for this to be slow-fast? I want some iterate, n, much larger than 1, so that if you take a bunch of iterates of t and then project, it's like you're just taking one step of the slow system S. So that if you take some large iterate of t and project, that's almost the same thing as first projecting and then looking at S. And so that's the slow dynamics. And then if you look at small iterates, so for n much, much smaller than big N, if you start with some point Z, and this projects to Pz, I want that the dynamics for small iterates stays close to the fiber over V, and that you can approximate this dynamics Tnz well by some system just on the fiber. So I want that for n less than n, Tn of x is nearly constant. And there's some t hat on this fiber. So that t hat approximates t. And I'm going to be very loose in terms of approximate and nearly, but you could try and set up a rigorous framework for this by saying something like this. You could take a limit of systems, and under some pathwise notion, this converges, and then these converge under just normal notions. All right, so this is one example where, again, P is just projection onto this coordinate. But for most of this talk, I'll look at a different example. So a slow-fast system that's a stochastic differential equation. And here's some time series and equations, but hopefully this will work, and I can show this in motion. Let's see. Okay, excellent. So here is x and y. So y is the fast variable, and it's given by this epsilon term is the scaling. That as epsilon goes to 0, the time difference gets bigger and bigger. And you have y minus y cubed, which has these stable points at plus and minus 1. And then you just have some Brownian motion here. So y is oscillating between plus and minus 1 because of this Brownian motion noise. And then it's forcing the x variable here. So x, again, goes between x equals 1 and x equals minus 1. And now the forcing of y means that as y is positive, it's forcing x to the right. And then if we wait long enough, maybe it'll switch. Yeah, and then as y is negative, it forces x to the left. So under these parameters, there's these two metastable states. There's the state where x is on the left and the state where x is on the right. And if you wait long enough, you probably don't have time to wait long enough. If it's, say, y is positive for long enough, it's actually enough to switch over to the other side. And so usually when I demo this is actually generated in the browser, so it's totally random. Often it's enough to switch over. Yes? Yeah. If you remove it, then there's 4 attracting fixed points. Actually, sorry, there'd only be 2 attracting fixed points. So if you'd removed all the noise, then y would go either to plus 1 or minus 1. And then if it's plus 1, it would force x to something near 1. And then if it's minus 1, it would force x to something near minus 1. So there, oh, sorry, now it switched over to the other side. Any question?
No, the question was only like, so if we move it without you, we have these 4 fixed points.
Yeah.
And on the other table, really, on the vertical, we have a real.
Yeah, so without the noise, it would look something like this. Sorry.
Yeah, but there is one direction more rebellion than the other.
Yes, because, yeah, A is close to 0. So the reason we're looking at this system, first off, instead of something like this, is that you can draw it in 2 dimensions. So it's a nice toy model that you can draw pictures of like this. And also what we want to look at is these multi-scale systems where you have sort of slow, medium, fast behavior. And so we can imagine that maybe x is slow and y is medium, and then this thing is actually already some homogenization average of an even faster system. That was our motivation for this map. And now this one actually switches quite often, and I want to analyze something that has a bigger timescale separation. So this value epsilon and everything I compute, I'm going to do now with 0.01. And if you do this, you can sort of notice it here that it's moving slightly to the left and slightly to the right. At the time scale we're running right now, it would take about 12 hours. I've never actually seen it. It would take about 12 hours for x to switch between these 2 states. So if you just calculate orbits, numerically, you have to calculate very long orbits involving all of the iterations of y to actually see this behavior. And so the question is, numerically, how do we analyze the system and what's going on without having to take these very long time series? All right, and the other thing is, here it's pretty obvious that this is the fast variable, and this is the slow variable. But if we distort our system, that's the other idea. If we just apply some change of coordinates to the system, then it may not be obvious. So later I'll look at this distorted version of the map. All right, so here's our example. And to analyze it, I'm going to look at properties of the transfer operator and the Koopman operator for these things. So let me put it up here. So here are my goals. You have some slow-fast system. You want to isolate both the fast dynamics and the slow dynamics. And you want to, the other thing is, what we're trying to do is if you have one of these complicated models, you want to know what's happening long-term in the future. You want to see this sort of, say in the example, switching between these two states. And you'd like to be able to model that without modeling all of the very fast oscillations. So that's another goal here, that we're trying to figure out the long-term behavior without modeling all of the fast oscillations. Like as an example, there's these models in climate science that people are trying to figure out what the Earth's climate is going to be like decades from now, right, in 50 and 100 years. And there's all these variables and stuff. So hopefully if you identify something that's changing really quickly, like cloud cover over the ocean, you can just eliminate that from your model and then analyze these things faster. All right, so I'll use these operators defined for the system. So we have the transfer operator, which is just given by the first equation up there. And the idea here is if you have some density, let's call it f dm, say with respect to Lebesgue, then the transfer operator associated to our system T is just moving all of this mass as where these points would go to under T. So this would be L Tf dm. And in our example, there's a stochastic component. So this is sort of on average where this mass is being moved, if you look over all the possible forward path. And then the adjoint of that is the Koopman operator, or the composition operator. And all that is saying is you just take some function, f, and the Koopman is telling you where that function is going to be in the future. Or, in the random case, the expected value of that function in the future. So for this system, we can go in and approximate these operators numerically and then look at their eigenvalues. So this is, in the first case, if you look at an eigenvalue of 1 for LT phi equals 1 times phi, this is telling you, if you write out the last equation here, that you're going to get the invariant measure for the system. So this is one of these techniques. If you want to figure out the invariant density or the invariant measure for some system, you can encode it in a matrix, this operator, under some numerical approximation, and then go through and calculate the leading eigenvalue on the operator. So if you do this under the right system, you actually observe all of the 4 places where the system tends to lie, and see that it's symmetrically going between the left and the right. And then for other eigenvalues, you look at LT of phi, where this is less than 1, then under time this will decay down. So this will be some sort of transient that, as you keep on evolving forward, will go away. So the next eigenvalue, if you compute it here, is a similar kind of picture, but now on one side it's positive and one side it's negative. And the idea in this system is you have this x minus x cubed, which is giving you a double well potential, and the invariant density is even between these two sides. And what the second eigenvalue is saying is the longest term behavior is if you have some lump of mass over here on the left side, then as you evolve forward in time, half of this mass will eventually come over to the other side. But as the eigenvalue is very close to 1, this takes a long time to happen. And then the next eigenvalue here is the next slowest decaying transient. And the idea is if you put some lump of mass right on top of this double weld potential, then it'll decay down to both sides. And you can see the eigenvalue, this one's very close to 1. This takes a long time to happen. And the next one is still close to 1, but it's larger. If you look at these logarithms, this is sort of the Lyapunov exponent of the system. This one's 0.01, and this one's 0.85. So there's a big change in time there. And also, you can look at the eigenvalues for the Koopman operator. So these are, if you look at the Koopman operator for something changing in time, say this equals lambda times s, this is saying that if you iterate forward, the expected value of f at t to the n is going to be decaying down to 0 at this rate lambda. And now, for these slow-fast systems, we can look at the operator both for the full dynamics t and the reduced dynamics s. So imagine you have an eigenvalue for s, ks psi is lambda s psi. So this is just saying, I'm going to write it without the expected value. This is just psi composed with s. If you had something like this, you could compose both sides with p. And now in the slow-fast framework I wrote at the start, this thing I said was well approximated by p composed with tn for some high iterate n. And so you get a psi of p here and a psi of p here. So intuitively, at least, it looks like this psi composed with p is approximately an eigenfunction of t to the n, because this equation's approximately true. And then it's not too hard to believe that it's also approximates an eigenfunction of t, and then the eigenvalue in this case would be the nth root of this lambda s here. And so n is supposed to be this high iterate, so in this case, this should be very close to 1. So what I'm saying is if this slow-fast abstraction is valid, even though we don't know in advance what this p is, this projection, our hope is that if we can reasonably approximate the leading eigenfunctions of the Koopman for t, they should all be sort of this form, where we're composing some function with the projection p. So we can compute these here, and indeed, that's the case. So here's one leading eigenvalue, and it's +1 on the left side, and -1 on the right side. And again, it's decaying very slowly, saying that it's very hard to move between these two states. And then if you look at the other ones, they get more complicated, but they all look like there's some function. They all look like we're projecting down from this space down onto some one-dimensional set and then evaluating some function on that. And you can even go and look at the level sets for these things. And even though they're all different eigenfunctions, all of their level sets seem to be lining up together. Is that showing up? Sorry, let me do that again. So that's the idea for this approach. We want to know what this projection is. And numerically, at least, we can get some approximation of it by these eigenfunctions. So we're trying to discern this function from the full space Z to X. And what we have are these eigenfunctions, let's say psi I, calculated from Z to R. And now if I take several of these, psi 2 up to, say, psi m, this is some projection from Z to Rm minus 2. And this product I'll just call phi hat. And I'm assuming each of these phi i's is roughly of this form, where these are functions what am I using? X, okay. Rm minus 2. So if the eigenfunctions for the Koopman of S, if I take enough of them, hopefully this will approximately give us some sort of embedding of our slow space into Euclidean space. And then if that's true, then this phi from Z to Euclidean space should approximate P from Z to X, using this as the identification. Okay. So in this case, it's simple enough. We only have one fast dimension, one slow dimension. And you can just take this first eigenvalue here. So phi 2. Yeah.
All the time you are trying to define X and P.
Yes.
So you have P, just if you're dynamic and you want to identify who's going to be the projection and where to project.
Yeah.
But in the example that you're giving, you have an a priori knowledge of where you have to project.
I mean, I do because I set up the system. So this is some toy model, and we know that we want to project onto the x-coordinate. But all of these techniques, this calculation of the eigenfunctions on the full space, don't actually use any a priori knowledge of the x and y coordinates.
Okay, so it's not only identifying the space, also it's letting you where to project.
Yes. Yeah, that's the idea. You have no idea a priori what P is, so you have to construct it somehow, and this is the technique we're using. Actually, let me talk about that very briefly here. So how are we computing these things, and why, even if we don't know what this projection is, why would we be able to discern these leading eigenvalues? And so numerically, you want to approximate this transfer operator, which is defined by LF composed with G equals F. Sorry, this is times. F times G composed with T dm. And for the definition of L, this needs to be true for all F and G on some Banach space, say L2 of Z. Here, we're just doing it in the Hilbert space. And the numerical techniques, almost all of them, the idea is you don't do this. You just take some finite dimensional subset V. So this is like a Galerkin approximation to this. And most of them have this form, and the trick is to figure out what the best subspace V is to use to approximate the system. And in this case, it's using Ulam's method. And the idea is, here I'm just drawing it as a bitmap. So the functions are all of the functions that are constant on every little rectangle that I'm drawing. And so in this finite dimensional space, if you do this approximation, you'll get some matrix, the n by n matrix, that's approximating the operator. And then you want to find the leading eigenvalues of this matrix. So in this case, this is a 200 by 200 map. So this is a sparse 40,000 by 40,000 matrix. And the simplest way to find a leading eigenvalue is just the power iteration method. So you start with some random vector v and compute AV and divide by its norm, and then you can just iterate this process, AN. And this will converge down to the leading eigenvalue. And of course, this is the simplest thing you can do, and it doesn't work too well, especially in a case like this where you have other very slowly decaying things. It's faster than evolving your system because you're just doing matrix multiplication instead of actually calculating a bunch of orbits once you have the matrix. But there's more sophisticated methods. So for instance, if you took a bivector, U wedge V, and did the same thing, this would converge to the wedge of the first two, the leading eigenvectors. And the convergence of this one is on the order of lambda 2 over lambda 1 to the n, where lambda 2 is this eigenvalue here. This one is lambda 3 over lambda 2 to the n. Basically, you have a lambda 1 here, and they cancel. And here. Sorry, so this wedge will be going to this eigenvalue, so this eigenfunction with this eigenvalue here. And then the next leading eigenvalue for the wedge project will be lambda 1 over lambda 3. And so those cancel. And here, you can just look at the values, and it would be approximately 80 times faster. So you're exploiting the linear structure of the transfer operator to sort of get to the long-term behavior of the system faster. Right? Like let me go back to this picture. You're trying to find this eigenvalue, say, and you know that your error is basically mostly due to this one. And so because of the linear structure of the transfer operator, you can account for that and converge much more quickly. So, I mean, there's been tons of work in eigenvalue systems solving for these leading eigenvalues of these sparse matrices. And they do things that are sort of like this, but much more sophisticated. They'll take other subspaces and add in vectors and remove vectors depending on the rates. What I'm trying to say is that the real issue is trying to convert your system into some sort of matrix. And then once you have a decent matrix, you can find these leading eigenfunctions very quickly.
So you have this, for instance, you apply your scheme E and N.
Yes.
To the partial hyperbolic model that you put in the beginning.
Yeah.
We know that S, X is the real line, and the other dynamical translation.
Yeah.
So, okay, but suppose that you don't know a priori, and you do your scheme of using the transfer operator, etc. To be really fast to identify the path. So, but how does it work? What happens? You apply instead in your model that you're doing this, you use the partial hyperbolic.
Okay, so I was working on this just before I came here to try and actually do an example on T3, and I mean I could compute the eigenfunctions, and they look like that. They were, you could find these tori, and it was invariant, sort of in the hyperbolic direction and changing in the slow direction.
So the transfer operator identified like in a shot everything.
Yeah, that's the idea. I mean,
Or the transfer operator where everything is very tame.
sorry?
No, they say that you, in the partial hyperbolic, you know that you know everything. Who is E, who is S, who is the projection, etc. So the question is, does the transfer operator give that really fast, immediately?
So you have to build your matrix, right? And I mean, in that case, it's an invertible map. So the transfer operator, if you actually looked at the transfer operator, it wouldn't have these nice eigenvalues, but the numerical method kind of adds diffusion to it, so you do get these eigenvalues. And so you can compute it. I mean, you have to compute these integrals, which are basically just you take some set. some pixel, and you iterate forward and you look where that pixel intersects. So you can do it. You can do it in parallel. You can actually do it fairly quickly. And I'll go to the distorted example soon enough, and you can see that even when we don't know the directions, you can identify these things. All right, so here was our eigenvalue phi 2. And so we have this approximation for the projection P. And now I want to be able to sort of identify what is the fast dynamics and check that it's actually faster than the slow dynamics. And so what I wanted was this function t hat on this fiber. So that t hat was defined on the fiber and it was close to the full dynamics. And so if you start with some point, sorry, here I'm assuming P is approximated by some eigenfunction like this. If you start with some point Z and apply T, you'll get something that's almost on the fiber, but not quite on the fiber. It might be moving slightly, and that's where this slow motion comes here. And you just want to project back down to get T hat. So the issue is Z is on the fiber. So if you look at phi of Z, it's going to be equal to V. And then phi of TZ, you might be slightly off the fiber, so it's no longer equal to V. To get back on the fiber, you just need to get it so it's equal to V again. So you just flow by the gradient in this case. This is sort of the simplest, shortest way to get back onto your fiber. So that's what we do numerically. Flow by the gradient V until phi of this flowed value is V. So you can define your dynamics on this submanifold this way. If you have something in multiple variables, it's slightly more complicated, but it's basically the same idea. And now you can analyze the dynamics here. You can look at a bunch of points and see how much they're changing and verify that you're actually approximating this validly, that this change is small in comparison to the large gap. So we did that here. So you can apply the same spectral methods. You can approximate the transfer operator, the Koopman operator, and calculate these eigenvalues and eigenfunctions. And now, before I was arguing that the eigenvalues corresponded to the slow dynamics. It was capturing these slow changes. Here, this is the slow variable. But now, in this case, we've restricted down to this submanifold, so the slow dynamics no longer applies. And now all the eigenvalues here should be associated to the fast dynamics. And you can actually compare them. Here's some big, ugly table of numbers. And so to kind of verify that you have this multi-scale system, the idea is just to look at the leading eigenvalues of the full dynamics, and then once you've reduced, that there's some drop in the value. And so you can compute these chi values, which are just the log divided by time, and the chi values also to have the same general ratio, and this value around 10 to the 3, 10 to the 4 is approximately the time scale difference, so the difference in time between the fast and the slow dynamic. All right, so as Enrique was asking, in this example, we knew where our horizontal and vertical was. So to do things differently, we'll look now at this system where we've just rotated and bowed out the system. So now it's no longer aligning nicely with our grid. But everything we did, all our techniques, are completely agnostic of the coordinates. We don't use any specific coordinates. So if you do the same things here, in the distorted example, you can compute the invariant density. You can compute, again, the leading eigenvalues of the Koopman, and they're the same thing, just in these distorted coordinates. So you are getting, in this case, what looks like some projection of the full system down onto some one-dimensional subspace, and then you're evaluating functions there. So again, you can apply this technique to reduce to the fibers, analyze these things, and you get pretty much exactly the same eigenvalues up to numerical error. So it is like a coordinate agnostic approach. And then there were three things I wanted to do. I wanted to first test if you had this multi-scale behavior, check if you isolate the projection, simulate the fast dynamics on its own, and then the biggest thing, simulate the slow dynamics without having to capture all of the fast behavior. So the idea is we're going to assume we're going to assume that this limit system is some sort of some sort of drift diffusion process. And so what's left is to calculate what these alpha and beta terms are. And the idea is we have some approximation of P. If we look over some point, we know the invariant density for the full system. So we can populate this fiber with points according to the invariant density, and then evolve these forward by some time t to the n, which needs to be large enough that these spread out a bit, but it doesn't need to be huge. And so these start moving about on the system. You project down by p, and you get some ensemble of points here. You calculate the displacement from v to the mean, and that should approximate your alpha divided by the time that you're integrating. And the variance should approximate your beta. So you can do this. You can do it for a bunch of points. You can do it in parallel. And you get some functions. So here, for the undistorted system, we did this, and here's our alpha value, which is capturing, basically it looks close to x minus x cubed, which it should because that's the system we started with. And then here's some variance. And once you have these functions, you can actually just go and simulate orbits for this system, just sampling everywhere from this drift and diffusion process, and you get an orbit like this. And you can compare it to the full system. So here's a time series. I ran the full system for some long period of time. And when you do this, the time step is really small because you have to capture all of the changes in the fast dynamics. But then once you have your alpha and beta, you can compute the same sort of thing just for the slow variable in isolation, and you can do it with a much larger time step because we don't have these fast oscillations. And now these look similar to the eye, but you can actually go in and test, and we've done this test, that they have the same sort of statistical properties. This is now for the distorted case, so when I took my coordinate system and rotated and sheared it. And now because we're distorted, we're no longer projecting nicely on x. We're projecting somewhere, but it's not entirely clear where it is. And so you get something that's x minus x cubed in a different coordinate frame and some diffusion process. But again, you can simulate this out, and it looks very similar to the original system. So here are the three graphs. And again, to look at the statistics to see if we're actually accurately capturing the slow dynamics, you can measure the width of each of these gaps, and they should obey some kind of Poisson distribution because it's like you're flipping a coin, and if you come up heads enough times in a row, then you switch over to the other basin between x equals +1 minus 1. And so you can actually go through and measure a bunch of these gaps and check that they obey a Poisson process, which just is seen by being linear on this thing here, and they obey the same Poisson process. So at least for this simple system, our starting toy system, numerically everything seems to work. So here's my last graph. So, if I were at a physics conference, everyone would be happy with this last graph, but we're trying to do math, and we're trying to show that this thing is actually valid in some sense. So as I said at the start, there's these homogenization results. Yeah.
So in this idea of reduced system, you started with the initial model that it was an also here. You add something that it was alpha, the first coordinate,
Yeah.
this coordinate, the sheet. Okay. So you say, well, this convert when you take the iterates is kind of random motion, some leading there. Okay, good. So this is the reduced system that you want to start. But you have the property that the initial one was an also that is kind of ergodic or whatever. But in principle, in your fast system, you don't know anything about that. You only know that it's faster. You need to have some elasticity yourself.
Yeah. So these homogenization results, they have two technical names. There's something called the weak invariance principle and the large deviations principle. The basic idea is that you need to have some sort of theory that tells you your fast variable, if you start at some random point and start evolving and sort of look at the average of that, you need some sort of central limit theorem. So you start somewhere random, you evolve, it should start looking like, you average out, it should look like some bell curve, something like that. And this holds, it's been shown to hold for axiom A and Ossoff systems, Lorentz-like systems. But in general, it's absolutely true. You could have something that moves very quickly, but doesn't obey that kind of law. So yeah, so that's, if you have these slow, fast systems, usually in the homogenization theory, they're parameterized by some value epsilon, like in our picture. And as epsilon goes to 0, you can show this pathwise convergence. So you can show that if you take an orbit up here, it's moving faster and faster, and you project, in some rigorous sense, you can show how this process, after projecting, gives you some kind of drift diffusion process. And because of this, one consequence of the convergence is that the invariant densities converge. If you look at the invariant densities of this system as you take epsilon to 0, then over each fiber, it converges to the ergodic average of your fast dynamics T. And if you project down, it converges to the invariant density of your limit system. And so the invariant densities converging is like the leading eigenvalue of the transfer operator, the Perron-Frobenius operator, converging. So we know that, but what we're using in these techniques are other eigenvalues of the transfer operator. So in some systems, we want to know, say that the transfer operator converges, or the Koopman operator converges. And we can prove this, but only in very limited senses, in only very specific systems. So we want to show, in general, if this happens more. And even you have these systems where you have a fiber, what we want to show is that as you take epsilon to 0, that this fiber actually goes to the vertical. But again, that's a very difficult question, because this homogenization theory only sort of tells us about the density, and we have to develop more tools to look at these other things. And I think that's about all I wanted to say, so I'll stop here. We're a bit early, but I'm sure everyone would love 10 more minutes at the beach, so thank you.
Well, you can put something that is not ergodic on the file, the vertical.
Uh-huh.
Ergodic, and they iterate, so it looks like faster.
Yep.
But okay, so that do not have any cannot do the tree because it's fast, but it's not the quality. All you can do a fast and low system that where you cannot do the tree. So this is the question. Can you
So there's one system I didn't mention is like center manifold theory, where your fast system is just quickly converging down to a point, and then you're very slowly moving to equilibrium after that. And that sort of applies in the way I wrote this, but that's not the kind of system that we're trying to analyze. I mean, you might be able to actually, yeah, the Koopman in that case should actually give you the fast